So now let's go back to our extreme value problem. From the Feynman theorem, we see that if f is a function defined on omega, the extreme point can only be those points where the gradient is 0 or the gradient does not exist. The not differentiable point, the point where the partial derivative not exist, might also be local minimizer or local maximizer. But if our function is smooth, we will not encounter this kind of point. So the suspicious point is the critical point. That is, the gradient at that point is 0. So we need to determine whether the critical point is a local maximizer or local minimizer, or it is not extreme point. Okay, there are some examples where critical point is neither local maximizer nor local minimizer. We have seen such example in single variable calculus. Of course, you can also construct example for multi-variable function. I will give you an example. Consider f two-variable function. fxy is the multiplication of xy. Then the gradient of f is fx fy. The derivative which respect to x is y. Well, the gradient, the derivative which respect to y is x. So this f has only one critical point, the origin. This f has only one critical point, origin, and the f00 obviously is 0, but 0 is not local maximizer nor local minimizer, because f is 0 on the coordinate index axis, and f is positive here and negative here. So for arbitrarily small neighborhood of the origin, this small neighborhood contains a point where f is positive. It also contains some point where f is negative. So 0 could not be a local minimizer, local minimum. So the origin is not a local minimizer. So the conclusion is that it's not local minimizer of f. Although the gradient is 0, although the origin is a critical point, but it is not local minimizer nor local maximizer. Maybe I will. It's neither local minimizer nor local maximizer. Okay, so this tells us that a critical point is not necessarily extreme point. So we need to some criteria to distinguish this. Okay, for this we can apply the Taylor formula to give a very beautiful result. And this is the theorem. As in our study of single variable calculus, we use the Taylor formula to deal with this problem. Here in multivariable calculus, we can also use the Taylor formula we established in the last lecture. Okay, so suppose f is C1, C2. To apply the Taylor formula, we need second derivative, so we assume f to be C2. In an R neighborhood of A, where A is a critical point, we want to determine whether this A is an extreme point. The conclusion is that if the Hessian of f at point A is positive, definite, then A is local minimizer. The second, if the Hessian is indefinite, then A is not extreme point. Finally, if the Hessian is negative, definite, then A is local maximizer. Okay, so this is the a very clear picture of the one determine whether a critical point is extreme point. Okay, of course we also have the case that is semi. In addition to these three cases, we also have semi-positive or semi-negative. These two cases are complicated, require more detailed analysis, and we will not state the corresponding result here. Okay. Now we see how Taylor formula can be used to study this question, prove this theorem. So there is a function eta defined on the R neighborhood of the critical point A, such that the limit of this function divided by the norm square is 0. And the Taylor formula fa plus h is fa plus, we have a term here, okay, plus half of h transport Hessian h plus eta h. This is the Taylor formula we established already. So we consider the first case. The first case, this is positive, definite. Then the first eigenvalue is positive. So for small h, h less than r, we consider fa plus h minus, which is fa plus half of h plus eta h. Here the gradient term, the first order term, vanishes because A is a critical point of f. So the gradient of f at A is 0. So we don't need to consider this term. This term disappeared. Okay. So now we are here. We are here. And we use the first eigenvalue inequality to this to the symmetric metric, that is the Hessian. We see that this will greater than fa plus half of lambda 1 h norm square plus eta h. Okay, so So since the remainder eta satisfies this limit is 0, so we can try to have divided by the norm square. Therefore, for this reason, we continue to fa plus norm square hat of lambda 1 plus eta h square. This we denoted by phi h. Phi h is this. This two term, we denote this by phi h, a new function of h. Then as h goes to 0, our phi h, the limit of phi h is hat of lambda 1. Because phi h is the sum of these two terms, where the second term is related to the piano remainder, which is 0, goes to 0. And the first term is a positive constant. So this positive constant, hat of lambda 1, is the limit. So the limit is positive. Therefore, by the basic result in limit, I will state the result in next page. Okay, I stated there a proposition. If limit x go to 0, fx equal to some L positive, then there exists some epsilon positive such that fx is positive for x maybe I write in this way. Which means if the limit is positive, then finally the function is positive. Okay. I believe we have proved this result in single variable calculus in the mathematical analysis 1 for single variable functions. But using the same idea, you can prove this result for multivariable functions. Okay. So we need this result. So using this result, because the limit of pch is positive, there exists some epsilon positive such that if h, the norm of h is less than epsilon, then pch is positive. So for such h, for those whose norm is more than epsilon, for such h, the pch is positive. Pch is positive means that this is greater than fa when the norm of h is less than epsilon. Okay, so this means that as long as the norm of h is less than epsilon, fa plus h is greater than fa. But here is a, and a plus h are all the point when the norm of h is less than epsilon. So a plus h represent all the point in the epsilon neighborhood of a. So this is equivalent to say that for any x in the epsilon neighborhood of a, we have a h whose norm is less than epsilon, such that this x is a plus h, and the fx, that is fa plus h, is greater than Fa. Therefore, A is a local minimizer of F. So this proves the first result of our theorem.